Okay, so let me continue. Topic on elasticity. So today's topic is linear 3D elasticity. In the last lecture, I talked about one-dimensional elastic problem. So I gave you example on very simple spring. For that spring, the displacement become strain and external force become stress, right? And we found some free energy. If we take the derivative about strain, then we can find the stress, right? In 3D linear elasticity, okay, so the free energy of incremental free energy can be calculated by stress and strain, small increment of strain, right? Everything are same for the case, one-dimensional case. Only difference is that we are using the tensor matrix instead of a scalar value, right? And here I use some special operator. This means Ij and D strain Ij. So we have the same Ij and Ij. It means the operator of this definition of this operator is equal I equal 1, 2, 3, J equal 1, 2, 3, and sum. So it means we are multiplying the each corresponding component and sum all together. Understand? So stress 1, 1, strain 1, 1 plus 1, 2, 1, 2. So we are doing this calculation 9 times 1, 3, 1, 3. Okay. This is the definition of this operator. Okay. And the total free energy can be calculated if we integrate that equation 1 over 2 3 Here the C have a 4 on the bar, right? This one is 2 on the bar. Mean this is matrix or second order tensor, and strain is also matrix, second order tensor. This is a 4 on the bar. It means fourth order tensor. Fourth order tensor. In tensor form, Ij, Cij, Kl, Ekl. if we take the derivative of our strain matrix for that free energy, we can find out C and strain. Here C is a material matrix. So C is actually force of the tensor, which give us relation between stress and strain, right? Okay, and in tensor form, stress Ij equals Cij KL and KL. So it looks strange for you at this time. And C have a component Ij KL and base vector I, and this is a X, this is a tensor product J K L. So you can imagine the scalar, vector, and matrix, right? In your, but this force of the tensor, it's very hard to imagine in 3D space, right? But we can use. So force of tensor, four base vector. So you can think the force of the space. Okay, 3D, not 3D space, 4D space. So, how many components we have here? How many components? Number of components. So, the matrix C gives us relation between stress and strain. So, how many stress we have here? This is 3 by 3, right? This is 3 by 3. So 9 component, 9 component. So to make a linear relationship between both, how many components we have? 9, 9. So for example, here I have A, B, C. 3 components here. D, E, F. To make a relation, I need a 3 by 3 matrix, right? Then 9, 9. 9 stress, 9 strain. So we need 9 by 9, right? 81. So number of components is 9 by 9 or 3, 4. Because the I is changing from 1 to 3, J is changing 1 to 3, K and L is changing 1 to 3. So 3, 3, 3, 3. This is 81. So material matrix C have 81, total 81 components. But we know stress tensor is a symmetric. So stress tensor is a symmetric. Strain tensor is a symmetric. It means we have only 6 independent components for stress and strain because it's symmetric, right? So here 1, 2, 3. Once we know these 6, we can find other 3, right? This is metric. 3 diagonal, 3 off diagonal. So stress has a 6, strain has a 6 independent component. So number of independent component will be how many? 6 by 6. So component become number become 6 by 6. Then 36. So now you can use vector relation instead of that kind of complicated force of the tensor. So once you define stress equal stress 1, 1, 2, 2, 3, 3, 2, 1, 2, 2, 2, 3, 2, 3, 1. We can define like this. Strain 1, 1, 2, 2, 3, 3, 2, not 2. 1, 2, 2, 3, 3, 1. Actually, stress and strain was a matrix, but we can define that stress and strain with a vector, right? Why not? Then that force of the tensor become second order tensor, like that. 6 by 6, 36 component. It has a 36 component. Right? Okay, so sorry, this is wrong. I need to have a 2 here. 2, 2, 2. So this is engineering shear, right? 2EIJ equal gamma IJ, right? When I equal J is different, engineering shear. Here there is a very important thing. When we use the vector type of strain, we are using always engineering shear strain. We don't use we need to have a 2 here. But if we use when we use the tensor, we don't have that 2. So, okay, engineering shear strain and shear strains are different, right? Okay. Why we need to multiply 2 here? Huh? Why? So, because of energy. So, if we 1 over 2, okay, strain and stress. This gives us energy, right? And this become 1 over 2. So actually we don't need 1 over 2. It's the same. Strain, transport, stress. To make left hand side and right hand side become same, we need to multiply 2. Because here in the left hand side, both are symmetric. Even both metrics are symmetric, we have a 2 strain term. For this one has a strain 1, 2 and strain 2, 1. Right? Both are same. But here I am considering only 1. So when we calculate the energy, we need to multiply 2. Because we don't have here consider strain 2, 1. So because strain 2, 1 and 1, 2 is the same, so when you calculate the energy, I need to consider strain 2, 1. So I need to multiply 2. So if you expand both sides, you can check same. Okay, then we can calculate Cij KL by differentiating the stress Ij with the strain KL, right? And equal strain KL and free energy strain Ij, right? From this equation, right? If we take the derivative twice, we can calculate the material law C. And also, let's consider C KL Ij. So here Ij KL, I just switch the KL Ij equal Ij stress KL, right? Here, strain Ij KL, right? Let's compare the first and second equation. This part and this part. Is that same or not? Same, right? This component can be changed, right? Even if it's changed, it's still same. So we can think Cij KL equal CKL Ij, right? It means this material, the tensor, is a symmetry, has a symmetry for first two components and last two. Okay, so Cij KL equal CKL Ij equal we are saying this is a Maxwell symmetry. Maxwell symmetry. So in both of the tensor, first Ij and second ij. In second order tensor, that become this one. This is 1 is ij. 1 become kl, right? So it means this C matrix, that means C material matrix C is symmetric. C equal C transpose. Symmetric. Then originally C was 36. Then now C has how many components? Independent component that C have. How many? Because C is symmetric. On the diagonal, how many? 6. Okay, so your diagonal 6. And next maybe. 5, 4, 3, 2, 1. Right? Then 5, 21, right? 21. Not the girl group 21. This is 21. Okay. So now we have 21 independent components. Any question? Can you follow me? So I need to make a very important conclusion here. Let's say for linear elastic material, we have a relation between stress and strain, and strain has a 21 independent component. So once you have a linear elastic material, the material matrix have a 21 independent component. Then to find that 21 independent component, how many times do you need to perform experiment? At least 21 times, right? So you need to make a 21 independent experiment, right? And then you can calculate 21 components, right? Lot of experiments. So for all the linear elastic material, for composite material, okay, for steel, steel is linear elastic. For any linear elastic material, you need to do 21 independent experiment. So this is a general case. But now let us focus on special case, isotropic. linear elastic material. What's the meaning of isotropic? Isotropic. Isotropic has a meaning of direction. So here I have a material here. I'm gonna give tension in this direction with a 10 Newton. Okay, and this material deformed at its length change. So it was originally length 1. After changing, length become 1.2. With the same material, I give a 10 Newton in the other direction. Also length changed. Okay? Length become 1.6. So it means the material behavior is different. Okay? Depending on the direction, right? This is general case. So in this case, we are saying material is not isotropic. Also, we can think the other case. Okay? So here we cut the specimen like this. Also, we cut the specimen in this direction. So we can apply the 10 Newton in this direction. So the length change become maybe 1.3. So actually, in general case, the material behavior is different. Okay, depending on the direction. But isotropic material is a really ideal material. We just think the material behavior is the same depending on the direction. So we have a same length change, okay, for all possible direction in 3D, right? Then actually that kind of material did not exist, but we are just thinking, right? We are just considering that kind of material exists. So here, in this case, can consider non-isotropic case. Okay? But now only consider isotropic linear elastic material case. Because usually in engineering, we are thinking the older material is considered to be isotropic, right? Then the problem becomes easier, right? That's kind of assumption. This is the assumption. Okay? So isotropic mean or behavior that does not depend on specific direction. So you remember the invariant? What's the stress invariant? Some value, okay? That value was a function of stress component, right? And that value doesn't change, okay? Depending on coordinate system. So it means depending on the direction. So we need to have that concept, invariant concept. Actually for strain instead of stress, right? Same thing. Strain and stress have a linear relationship with C. So it means if we have a stress invariant, we have a strain invariant too, right? Because C is just constant metric, right? So this means elastic potential okay. So this is free energy, same thing. Elastic potential and free energy, and same thing, is a function of strain invariant. So we have three strain invariant. Trace, so EII, okay, 1/2 JI. So definition is the same to the stress, right? Exactly same. First one corresponding to hydrostatic stress, right? Here stress, this means stress 1 plus strain 1, strain 1, strain 2, strain 3. What does this mean in physically? What's that? Huh? Sum of the diagonal component of strain matrix, right? That was a volume change. You remember? That was a volume change. Anyway, so people did some experiment long times ago, and they finally represented free energy or isotropic linear elastic material with strain invariant like this: lambda over 2 trace square plus 2g 1/2 trace E like this. So here in strain invariant 1, this is strain invariant 2, right? So we can represent the free energy of isotropic linear elastic material like this. And here we have only two constants, lambda and g. Lambda and g. and their name constant. Okay. So now we have only two material constants. That become material constant, right? Because if we take this free energy, if we take the derivative, if we differentiate this free energy with the strain, we can find material law, right? So here we have only two material constants. So for linear elastic material have a 21 material constant, but isotropic linear elastic material have only two independent material contact, right? So our problem become much easier. Only two. And that strain energy if I expand this equation, it becomes strain 1, 1, 2, 2, 3, 3 square plus G something like that. Equation looks very wrong. And we know stress can be calculated from this equation. Right? So here, stress is a tensor, strain is a tensor, this free energy is a function of tensor. How can I calculate this equation? Can you do, you know how to do this? Right? You never try to do this, right? But this is actually simple. Yeah, for example, let me do that. The stress 1, 1 equal 1, 1. Okay? Let's take the derivative of this equation about strain 1, 1. What can you find? So, lambda over 2 and 2, 1, 1, 2, 2, 3, 3. Right? And plus G and strain 1, 1 here, right? And 2 strain 1, 1. This is stress 1, 1. How about stress 1, 2? Stress 1, 2. 1, 2. over there for the first term, we have 0, right? Plus G, okay, 2 strain 1, 2. That's it. We can do this job 9 times, right? And then we can make a matrix relation. So here stress 1, 1, stress 2, 2, 3, 3. Okay, so I need to give you this first. So actually stress, if you do that kind of job again and again, and finally we have this result. Lambda trace I plus 2G. This is result of differentiation. Or in tensor form, ij equal lambda kk ij plus 2g ij. So isotropic linear elastic material, we can calculate the full material matrix C equal okay. How about the first term here? We need to look at here, right? Lambda, E1. We need to look at E1. Lambda plus 2G. Right? How about second term? E22. Then lambda. E33 lambda. And about strain, this strain 0, 0, 0. Something like that. Because this is a symmetry, so we can also here put the lambda symmetry. So for the strain component 2, 2, this is isotropic material. So we can have a lambda plus 2g here. Okay, lambda plus 2g 0, 0, 0, 0, 0, 0. Lambda, something like that. How about 1, 2? 1, 2 doesn't have interaction with the normal strain, right? So here 2g 0, 0. This is the material matrix. Material.